We went to the moon 6 times. We planted flags, drove rovers across its surface, and brought back rocks. That was over 50 years ago. So why, with all our technology, all our rockets, all our ambition, have we still not set foot on Mars? What is it about the red planet that stops us cold? Is it the distance? The radiation? The sheer audacity of the mission itself? The answer is all of the above, and then some. Because getting to Mars isn't just hard, it's a challenge of a completely different magnitude than anything humanity has ever attempted. Space agencies like NASA and private companies like SpaceX have been drawing up plans for years. The blueprints exist, the ambition is there. Yet in 2025, placing the first human boots on Martian soil still feels frustratingly out of reach. Today, we're going to find out exactly why. The first thing to understand is scale, and how badly our intuition fails us when it comes to space. We see astronauts launching to orbit fairly regularly. For years, Russian cosmonauts rode Soyuz capsules to the International Space Station. Chinese taikonauts visit the Tiangong station. It all starts to feel almost routine. But here's the thing. Every single one of those spacecraft barely scratches the surface of space. The ISS orbits just 250 miles above Earth, roughly the distance from Las Vegas to Phoenix. That's low Earth orbit. It's space, yes, but it's the shallow end of the pool. The moon already pushes us far deeper. At an average distance of 236,000 miles, about 1,000 times higher than the ISS, it sits well beyond anything we call routine. The Apollo missions took 3 days just to get there. And yet, compared to Mars, the moon is practically next door. This is where the numbers start to feel almost absurd. Mars, at its closest approach, which only happens once every 26 months when the two planets align favorably, sits roughly 34 million miles away. At its farthest, the gap grows dramatically. We're talking about a distance approximately 1 million times greater than the trip to the ISS. Let that sink in. To put this in perspective, consider the leap from one mission to another. In 1962, John Glenn's Mercury 6 capsule rode an Atlas rocket, 120 tons, 95 feet tall, to an altitude of 124 miles. One astronaut, 5 hours, done. A decade later, Apollo 17 Saturn V stood 360 feet tall and weighed 3,000 tons, carrying a 50-ton spacecraft to the moon with 3 astronauts for nearly 13 days. From 1.2 tons of payload to 50. From 120 tons of rocket to 3,000. That's the leap from low Earth orbit to the moon. Now imagine the leap to Mars. One proposed crewed mission to Mars envisions 6 astronauts spending 174 days just getting there, 539 days on the surface waiting for the planets to realign, and another 201 days flying home. Total, roughly 911 days, 2.5 years away from Earth. And the math that follows is brutal. Compared to a 12-day lunar mission with 3 crew members, a Mars mission with 6 astronauts lasting 73 times longer would require approximately 150 times more supplies. Food, water, oxygen, medicine, all of it packed and launched from Earth, because there are no resupply options once you leave. Then there's radiation. Far from Earth's protective magnetic field, astronauts would be exposed to deep space radiation for the entire journey. And existing shielding solutions are heavy, expensive, and still not fully adequate. And equipment wear. On the ISS, a broken part can be replaced within days. On a Mars mission, if something fails, you work with what you have. No spare parts incoming. No rescue mission coming to find you. Every problem that seems manageable in orbit becomes potentially mission-ending 34 million miles from home. And all of that mass comes at a price, a staggering one. Every kilogram of shielding, every extra supply module, every backup system adds weight. And weight in space travel is everything. Because to move mass, you need fuel. To slow down at Mars, you need fuel. To lift off from the Martian surface and fly home, you need fuel. And to carry that fuel, you need more fuel. The numbers are almost difficult to believe. Estimates suggest a round-trip Mars mission could require somewhere between 850 and 1,250 tons of propellant. For context, the entire International Space Station, a structure that took over a decade and dozens of launches to assemble, weighs about 420 tons. The old space shuttle could haul 15 to 25 tons to low Earth orbit. Even Starship, SpaceX's most ambitious rocket yet, aims to carry up to 200 tons, a remarkable achievement, and still not enough for a single Mars mission on its own. This means no single launch gets the job done. A crewed Mars mission would likely require multiple flights, deploying propulsion modules, supply caches, living quarters, and cargo ships separately, then assembling everything in orbit before the crew ever sets off. Consider that during the entire Apollo program, the mighty Saturn V flew just 9 crewed missions to the Moon. A Mars mission might demand that level of effort just to get the hardware into position. Some scientists propose a potential solution: manufacturing fuel directly on Mars, extracting it from minerals or gases buried beneath the Martian surface. It's an elegant idea, but it remains exactly that, an idea. No extraction or processing system has ever been tested in actual Martian conditions. Until that changes, the only reliable option is hauling every drop of propellant from Earth. But fuel isn't even the most unsettling problem. What happens to the human body during 539 days of weightlessness? We know the answer isn't good. Bones weaken, muscles deteriorate, cardiovascular systems adapt in ways that make normal gravity feel crushing upon return. We don't yet have spacecraft capable of simulating gravity. No spinning cylinders like those imagined in science fiction. That means the crew would arrive at Mars after nearly a year and a half in microgravity, then immediately be expected to function on a planet with real gravity, in a hostile environment, with no rescue coming if something goes wrong. And then there's the silence. 2.5 years is a long time to be sealed inside a cramped, pressurized vessel with the same small group of people, under relentless stress, cut off from everyone you've ever loved. Even at the speed of light, a radio message between Earth and Mars can take around 8 minutes each way. No real-time conversations. No voice of mission control in your ear when things go wrong. Just delay, distance, and the vast indifference of deep space. Once on Mars, the situation doesn't get easier. Astronauts would live in pressurized habitats, potentially even smaller than the spacecraft that brought them there, venturing outside only in full suits, never truly free, never truly safe. So where does that leave us? Some optimists argue that the technology already exists, that what we lack isn't capability, but political will and funding. And there's truth in that. Human ingenuity has overcome impossible odds before. But scientifically speaking, the gap between where we are and where we need to be is still very real. The engineering, biological, and psychological challenges are not minor hurdles. They are walls. That said, walls have been broken before. NASA believes the first humans could set foot on Mars before the end of this century. Others are far more cautious, warning that decades of development still lie ahead. And then there's Elon Musk, who has publicly declared his intention to send humans to Mars before the end of this decade. So the question is yours. Is Mars within reach? Or is it a dream that will forever stay just out of grasp? Are we bold enough, resourceful enough, determined enough to make that crossing? Leave your thoughts below. And if this journey into the cosmos sparks something in you, a like goes a long way. Subscribe if you haven't already, and we'll see you in the next one.